Hello everyone. Today I'm going to talk about multimodal pre-training for dense video captioning. Let's start with the motivation first. So we know that video consumption has been growing in the last years, and in fact, the average person is forecasted to watch 100 minutes of video per day in 2021. Instructional videos are a big part of it, and people go to YouTube for how-tos, tutorials, and for learning new skills. But videos are inherently hard to skim through, and I find myself repeatedly clicking on the timeline to find the part that I need. Users could really benefit from metadata such as timeline annotations, and in fact, search engines such as Google have started linking to key moments in videos. For instance, they will show those different steps for each videos. Those steps are created by the content creators to help the user. So the question is, how can we generate those timeline annotations automatically instead of requiring the content creators to make them? We can decompose generating timeline annotation into two tasks: segmentation of the video into steps and video captioning of each step with a label. In this work, we'll focus exclusively on dense video captioning, and we'll assume that the video segments are given externally, either hand annotated or by another algorithm. We will consider two tasks here: multimodal video captioning. We start from the video. We will run some automated speech recognition to get the ASR data, the transcript on the video, and we will output a short caption for each section. We also consider text-only video captioning, where we are not allowed to use the video features, but only the ASR as input. So, summary of contributions. We propose a new dataset, video timeline tags, which is designed specifically for timeline tagging. And we explore various combinations of pre-training and fine-tuning objectives. We obtain state-of-the-art results on UCook2. So let's start with the datasets. Those are the datasets that we use for pre-training and fine-tuning. The first four are for pre-training. The last two are for fine-tuning. Yes, so UCook2 and video timeline tags are the two datasets we'll use for fine-tuning, but also for evaluation. Let's start with UCook2, which is a popular dataset for video captioning. Here are some examples here. You can see that all the videos are cooking, and the steps are like recipe steps. So for this application, there's a number of issues. The first is that UCook2 requires limited generalization because each video is split between training and testing. It's guaranteed that there will be no unseen recipes in the test split. Also, there are only cooking recipes, and the captions are kind of lengthy, which is not very good for timeline tagging. This is our new dataset. You can see that there's a variety of activities ranging from makeup, home repair, arts and craft, to car mechanics and more. We require stronger generalization because we didn't explicitly enforce that the activities are already in the training split, and there are no videos in common between the different splits. Also, the captions are fairly concise with an average of 3 words per caption. Because parallel data, so the two datasets we saw had ASR video and caption, those datasets are expensive to acquire. They require expensive annotations. We also consider unpaired datasets for pre-training. So we consider those datasets, YouTube 8 million, How-To 100 million, for pre-training on the ASR plus video type. And we will also consider those text-only datasets, Recipe 1 million and WikiHow, to pre-train the caption part of our model. So you can see that those are like steps for different tutorials, while those are similar to the potential input. Let's talk about the architecture now. So our architecture is fairly standard. It's a transformer-based architecture consisting of separate encoders for ASR and video. So we have the ASR here, the video here. They can cross-attend with cross-model attention. And we have a text-only decoder to predict the captions. So it's represented here, and it can attend both to the text features and to the video features. Throughout this presentation, we'll just simplify this architecture with this data flow diagram. So here we illustrated how to use the model during inference. So for video captioning, we feed ASR and video features as input, and we'll get captions as output. Pre-training and fine-tuning objectives. We investigate various combinations of them, and we'll give the results after we present the different objectives. So let's start with the pre-training objectives. We consider both text-only pre-training and multimodal pre-training. So in text-only pre-training, we'll use either caption style or ASR transcript data, while in multimodal pre-training, we'll also consider ASR plus video data, which is something we usually get when we use video datasets such as YouTube 8 million. Now for fine-tuning, we have those two objectives that correspond to our final task to solve, ASR to caption and ASR plus video to caption, depending if we do text-only or multimodal fine-tuning. We also consider those two objectives, reverse fine-tuning, text-only, and multimodal. And this consists in solving the reverse task, starting from the caption and hallucinating some meaningful ASR that would correspond to it. And we'll see that it can help in some cases. So let's start with the pre-training objectives now. We use masked sequence-to-sequence pre-training, which consists in jointly pre-training the encoder and decoder to reconstruct a masked subsequence. So here we'll feed a sequence to the encoder. Let's say it's ASR. We'll remove some of the words. The decoder can attend to it, and it will have to reconstruct the hidden part. We help the decoder with teacher forcing, so it's just the missing part shifted one word to the right. We know that masked pre-training has been successfully applied to sequence-to-sequence problems such as unsupervised machine translation and summarization tasks. In comparison, methods such as BERT or language model approaches can only pre-train the encoder or the decoder separately. So this is why we picked the masked pre-training objective. We'll apply it on ASR and caption datasets. Now, the masked pre-training objective is only text only, and this will not teach the encoder how to use the video. So we extend mask to the multimodal setting by doing the simplest thing. We'll allow the encoder to condition on the video. And by that we mean that we'll have this separate video transformer that they can cross-attend to each other. So instead of having mask for ASR and caption, we now have mask for ASR plus video and caption. We'll only attempt to reconstruct the ASR here because the video will only have to be used in the encoder part in the end task. There's one problem with this approach is that potentially the transformer could just learn to use the ASR and ignore the video, which is why we investigate randomly dropping the ASR features to force the encoder and decoder to attend to the video features. We will denote this as a mask drop in the experiments, while the conditioning approach will be denoted mask vid. We also investigate another approach. It's that we will sample one ASR and one video segment, and the encoder will have to predict if the two are aligned, they occur at the same time, or if they are not aligned, which one occurs first. So we will combine this objective with the text-only mask, and we'll denote this as mask line in the experiments. So this is all for the pre-training objectives. Now in terms of fine-tuning objectives, we investigate, so we start of course with the final task objective. We take ASR and video as input, and we have to output the caption. So this is for VIT or UCOOK2. But we also investigate solving the reverse task, which is to take caption as input and hallucinate the original ASR. So we have two variants of it. And we'll show in the results that it's a little bit helpful. Oh yeah, and those objectives can be applied to the text-only setting as well. You just have to remove the video inputs. Let's see some example predictions now. So on UCOOK2, we can see that there's a trend in general. So here we have the ground truth. Here we have the results with no pre-training, and those are the results with the text-only mass pre-training. And you can see that there's a lot more recent, decent predictions when we do the pre-training than without the pre-training. Those are the results on VIT. Those are the better results. You can also see that using pre-training helps in terms of quality of predictions. Those are bad predictions. So you can see that it's a bit better still to use text-only mass pre-training. Okay, let's talk about the quantitative results now, the scores, and some ablation study to better understand which components are useful. Those are results on UCOOK 2. Here are older and more recent results from the literature. This is the best state-of-the-art until us. So the first thing is we do get state-of-the-art results with our method using multimodal pre-training or text-only pre-training. The main gain here comes from, so let's look at the Rouge score. This is usually the score that we look when we are doing summarization tasks. We get about a 3 or 4 Rouge score increase compared to not doing pre-training when we are doing text-only pre-training. We get a little bit more score when we are doing multimodal pre-training, but it's not clear if multimodal pre-training helps that much or which type of multimodal pre-training, alignment, video mass, or video mass with dropping ASR, which one is the best. We can also see that all metrics here are kind of close to the human performance except the decider score. So maybe this might say that the decider score is better. It's not very clear. Oh yeah, one other thing is that we have compared results with using the video and without using the video. You can see that the difference is very small. So clearly so this is video, this is no video. So clearly most of the score comes from just using the ASR. Those are the results on VIT. We have 2 subsets, all the activities and just the cooking activities. And again, the largest gain comes from using text pre-training versus no pre-training. Here we have the gain in Rouge score for the 2 data sets. Using multimodal pre-training still helps a little bit more, but the difference is kind of marginal. And video helps a little bit, but not consistently. So we also conducted an ablation study to further understand the effects of the different components. So first we have tried reducing the number of layers for the decoder, and there's not a lot of difference. And I guess the reason is that the fine-tuning datasets are still fairly small. So there's not a lot of difference, but using more layers is marginally better, especially in the case where we are not pre-training. We have also experimented using different video features. In this work, we're using 2D features. We have also tried using S3D features, but comparing those 2 lines, you can see that the difference is kind of small. So it's not too important. We have also experimented 2 types of bidirectional fine-tuning. Not much difference either. One question is, are the video features too weak? And to answer this question, the easiest is just to look at the scores for the pre-training task. We actually get 90% accuracy for alignment and 80% for ordering on YouTube 8 million. For how to 100 million, we get 87% and 71%, where the random guess would always yield 50%. So this suggests that the video features are reasonably strong and that the findings are not due to weak visual representations. Conclusion. We have proposed a new data set, video timeline tags, specifically for the timeline tagging application to help users navigate videos. We have investigated many combinations of pre-training and fine-tuning objectives, yielding state-of-the-art results on UCOOK 2 and a strong baseline on VIT. The best results use multimodal pre-training, although significant gain is observed due to just using text-only mass. Though the video features have been shown to be strong, we still get strong results even without using the video with just the ASR as input. For future work, we'll investigate using end-to-end learning for the video features instead of using pre-trained video features. We'll look at more pre-training objectives, investigate ways to deal with optional inputs, maybe just video only or ASR only, and we'll try to leverage on-screen text as well. Thank you.